Hello everyone, my name is Mingda Zhang, and today I'm very excited to share our work titled BasisNet Two-Stage Model Synthesis for Efficient Inference. This is joint efforts with many collaborators while I was interning with Google Research. On-device machine learning has been an active research area in the past few years as it plays increasingly important roles behind various mobile applications. Prior work has attempted from different perspectives to improve the design of convolutional neural networks in order to achieve more efficient computation on edge devices. In this work, we present BasisNet, which leverages dynamic model synthesis to efficiently generate input-dependent specialist model from a collection of base candidates. The synthesized model is specialized at handling the given input, thus can give more accurate predictions. Multiple prior work have explored the idea of conditional computation, as it has been proven effective for improving runtime efficiency during model inference. In this work, we demonstrate the idea of model synthesis and show that with proper training, this simple idea can still achieve state-of-the-art performance. We illustrate our model design with an example. Considering a classic image classification task, and the input images may be of varied difficulties. For a lightweight model, it may be able to recognize the easier targets, in this case, distinguish cats from dogs, but it is also very easily making mistakes for the more challenging inputs, like telling the fine-grained breeds between dogs. To improve the performance on such difficult cases, we design a model synthesis strategy leveraging the knowledge from the lightweight model. Specifically, when the initial prediction is uncertain, the lightweight model will produce a group of combination weights, which will be used to guide the linear combination from a collection of base models. The synthesized model is thus directly tailored for the specific input and can better deal with the subtle differences. We find that the entire BasisNet can be trained end-to-end without using additional annotations, and the lightweight model can automatically learn semantically meaningful strategies to guide the second-stage model synthesis. In addition, the two-stage design naturally supports early termination, which means the model can skip part of computation when the inputs are relatively simple. This technique can further boost the performance under limited computation budgets. We choose ImageNet classification task as our testbed and perform extensive experiments with mobile nets. Specifically, we retrain all the models under identical conditions for fair comparison. We build BasisNet with different generations of mobile nets as backbone and altering the multiplier to obtain lightweight model and base models. From the accuracy-efficiency trade-off curve, it is quite obvious that the BasisNet has clear advantage over mobile nets. We also show that by increasing the number of base models, the model synthesis can be more effective. We also perform on-device latency measurements on real physical devices and find similar conclusions. From our experiments, we find BasisNet is more difficult to train, partly because its high model capacity can easily lead to overfitting. We apply multiple regularizations, including dropout on model candidates, more aggressive data augmentation, and knowledge distillation. We also use other tricks for more robust training, such as warm-up during model synthesis. We emphasize that these techniques are critical to fully unleash the power of BasisNet. Different from previous work, our lightweight model is highly efficient but still fully fledged, thus it's naturally compatible with early termination. More specifically, the model can selectively skip second stage for relatively easier input images. We calculate the entropy of predicted probability and use it as a proxy for confidence. We find that the prediction accuracy is inversely correlated with the confidence. For example, with a threshold of 0.7, BasisNet can skip nearly 40% of all images in ImageNet validation split, while still remaining an accuracy of 80%. However, the average computation cost can be significantly reduced to less than 200 million multiplication additions. We visualize the combination coefficients from lightweight model and find some interesting patterns. For example, for visually similar categories, the coefficients of high similarity indicating that a same specialist will be synthesized. On the other hand, when the objects have vastly different appearances, the specialist synthesizing signals are also very different. We also check the categories that most strongly activate individual-based models to better understand the synthesis procedure. We find that even subtle differences can be captured. For example, base number 14 and base number 2 both handle dogs, but one focuses more on the fluffy dogs, while the others deal with smooth-coated breeds. We also experiment with various perturbations to the model combination signals to validate the effectiveness of synthesized specialists. We observe significant performance degradation with all types of perturbations, showing the importance of following correct model synthesis. Thank you for your time.